Hi everyone. When I was putting this talk together, I talked to a bunch of people and I said, I'm giving a talk in Chicago. How can I pander to the audience? And they said, well, in Chicago, the city has a flag and it's everywhere and people love it. And I said, do they love it so much that they would get angry if I were to desecrate it on my title slide? And they said, no, probably not that much. And I said, perfect. So I'm Joel, and I am the Fizz Buzz and Tensorflow guy. That's not all I am. I'm a research engineer at the Allen Institute for Artificial Intelligence. We're hiring. We're hiring in Seattle, actually, which is where we're located. But it doesn't get cold there in the winter. And it's actually really easy to find authentic Seattle-style pizza there, unlike here. But we're not very good at sending our governors to prison. I'm working on it, but we've got some catching up to do. Before that, I was a software engineer at Google, and I did data science at a bunch of startups. And as mentioned, I wrote a book. You can see it. You should read it if you haven't. It's pretty good. Right, so I'm here to talk to you about Fizz Buzz. In case you're not familiar with it, it's a pretty simple programming problem. Write a program that prints the numbers from 1 up to 100, except that if the number is divisible by 3, instead of printing the number, print Fizz. If the number is divisible by 5, instead of printing the number, print Buzz. And if the number is divisible by 15, instead of printing the number, print Fizz Buzz. So that's the extent of the problem. It's not that complicated. But some software engineering places use it as a weed out problem in their interviews, figuring that if you can't solve this problem, then you're probably not much of a software engineer. Not that being able to solve it proves that you are, but not being able to solve it demonstrates that you really aren't. And so the reason I'm here is that I wrote a blog post about a guy, who I called me, who goes on a job interview and gets asked to solve this Fizz Buzz problem and feels moderately insulted at being asked to solve this Fizz Buzz problem, so decides to dive into it and solve it using TensorFlow, very obviously to his interviewer's wishes. It's a pretty good blog post. I encourage you to check it out. The first draft of this talk was me standing up here reading it to you, but the people I ran that by didn't like it, so I decided not to do that. But to sum it up with a meme, solved Fizz Buzz using TensorFlow, didn't get the job. But there's more to it. You should check it out. Anyway, why that blog post? I blog, like 4 times a year. Why that one? Well, I saw an online discussion about what's the stupidest way to solve Fizz Buzz. And I thought, I bet I can come up with a stupider way than that. Came up with a stupider way. The blog post kind of went viral. Jan LeCun tweeted it out. Jeff Dean shared it on his Google+. Everyone got really into it. And it's kind of a frivolous thing to use my 15 minutes of fame on, but that's okay. Got to use it on something. And so because one of my big heroes is Andy Kaufman, I wrote it in a way that it's kind of hard to tell if it's a true story or if it's not a true story. And in fact, at work last week, people are like, did that really happen? I'm like, I'm not going to tell you. But, and so because of that, the comments on the blog post actually got pretty good too. Where people started arguing about whether they would hire me. And then other people leapt in to defend me. One guy called me a expert, which I don't think I've ever been called before. So that was pretty exciting for me too. But as probably most of you know, this has a really simple solution. If you're doing Haskell, like I like to do, it looks like this. And since this is PyData, here's the equivalent Python solution, which looks pretty identical. So that's really the extent of Fizz Buzz as a problem. But I've still got some time left. So as a computer science problem, as a programming problem, it's not that exciting. But as a machine learning problem, it's actually kind of interesting. So machine learning, we want to build a model that will take an input and predict some output. What will our output be? I thought about it here. I said, you know what? There's 4 cases. You say the number as is, you say fizz, you say buzz, you say Fizz Buzz. So one natural way to represent that is a vector of length 4 that's the predicted probability of each of those 4 cases. Seems like pretty good, so that's what I went with. And once we do that, we can define a ground truth function that looks a lot like our solution to the problem itself. If it's divisible by 15, put a 1 in the 4th spot. If it's divisible by 5, put a 1 in the 3rd spot, and so on. And so this is the function that we want to learn with the machine learning model. Now that we know what we want to predict, we have to decide what are we going to use as our features. As I'm sure a lot of you know, feature selection is a difficult, important part of solving machine learning problems. Here, one thing we could do is we could cheat. And what do I mean by cheating? I mean, here we know that divisible by 3 and divisible by 5 are the essence of the problem. And so we just use those as our features. One of our features is this thing divisible by 3? Is this divisible by 5? And so, maybe it's not cheating, maybe that's just being clever. So what would that... Do you need to do anything in the back for this microphone, or is it good to go? Okay, great. So one thing is for any number, just create an array that has, is this number divisible by 3? Is it divisible by 5? And then I stuck a 1 in there to make the math easier as well. And so if you use those as your features, it's really easy to come up with a solution. Here it's a simple matrix multiplication. It can be a Fizz Buzz, as I'm sure most of you guys know. And then you just do that multiplication and pull out which is the largest of them. This is not a machine learning solution because I came up with that matrix by hand, but it has a very machine learning kind of feel to it in the sense that taking these inputs, multiplying them by a matrix, and then looking for the biggest output. It's hard to imagine an interviewer who wouldn't be impressed by even like a simple solution like that. And now you're probably staring at that being thinking, well, what the heck is that, and where do those numbers come from, and how on earth is that a solution to Fizz Buzz? And so all that is if you think of a divisible by 3 axis and a divisible by 5 axis, it's actually just measuring how far in each of those 4 diagonal directions the input is, and so whichever one's largest gives you the right case. Clever. It says clever on the slide. And so then, what if you're not that clever? In this case, because we know about the problem, we know that divisible by 3 is important, divisible by 5 is important. But what if we didn't know that off the top of our heads? What if we just had the data and not the rule behind it? One natural thing to try, the first thing that occurred to me to try, was just turn each number into binary. So if you want to do all the numbers up to 1023, that just gives you 10 zeros and ones, and that can be the input to your model. In the comments of the blog post, someone else suggested doing a one-hot encoding of the digits. So here, the first row is a 3, the second row is a 1, third row is a 5, and so on. So then you turn a 3-digit number into 30 zeros and ones. So I decided I would try both of those. And then because we're good kind of data scientists, machine learning practitioners, we don't want to train on our test data. So if the goal is to do this for 1 to 100, let's train on data that's not 1 to 100. So binary, the rest of them is 101 to 1023, decimal 101 to 999. And then we can use separate training and test sets. Who knows how neural networks work? Everyone? Someone? No one? I'll go through it real fast in case a few people don't. But basically, you get some inputs. You take those inputs, in this simple case, you multiply them by some weights. you do some computation on the inputs, and you apply an activation function. So in your stereotypical neural network, you multiply your inputs by weights, you add them up, and then you pass them through a sigmoid function, although no one does that anymore, or a ReLU unit or something. But anyway, this is how neural networks are basically set up. And so the talk is called Fizz Buzz and Tensorflow. So let me walk you through the extent of what I know about Tensorflow, which is mostly contained on this slide. You need to do some imports, and those are the standard conventions. You set up a couple placeholders for your data. You define some parameters you want to learn. You define some parametric model of your data and your parameters. You apply the model to the symbolic variables. You set up some training operation by minimizing some cost function. You create a session. You initialize variables. You train using data. So as you can see, that's a lot of code, and I actually didn't even say what the model was yet. So that's just before I've even written out my model. So since I wrote the blog post, I've gotten into Keras, which is a much nicer API that sits on top of TensorFlow and also Piano. And so the rest of this will be done in Keras, but I use the TensorFlow backend, so it's still in TensorFlow. So compared with what I just showed you, here's the equivalent one slide for Keras. Again, you import a couple things. I want a sequential model and some layers. Here I've actually defined the model, a dense layer, ReLU activation, a dense layer, and softmax. Don't sweat it if you don't know what all those things mean. I compile the model by saying, here's the optimizer I want to use, here's my loss function, and then I fit the model. So even if you know nothing about neural networks and deep learning, it's pretty clear that that's a much simpler and friendlier API to use. And it's easier to iterate on and get things to work. So that's what we'll be using. But Fizz Buzz and Keras didn't have the same ring to it, so I left the talk titled as is, and I hope no one's super disappointed about that. And then the other thing I just struggled with was, okay, I'm making all these predictions. How do I want to visualize the results? And what I came up with, it's not easy, but it's kind of the best I could. So from left to right, those are the numbers 1 to 100, which we're making our predictions for. And then there are 4 vertical rows. The first row is number as is, second row fizz, third row buzz, fourth row Fizz Buzz. And anytime you see a black dot, that means we predicted that output correctly. Anytime you see a red dot, that means we predicted that output incorrectly, and the blue dot is what we should have predicted for that number. So here you can see 1 was predicted correctly. For 2, we predicted buzz, because it's in the third row. But we should have predicted just the number itself, and so on. So stare at this graphic for a minute, because there'll be a bunch of these. And then, because those are hard to make sense of, I've also got crosstabs, as you can see at the bottom right. Each row is a prediction. Each column is an actual. So numbers along the diagonal are good. Numbers that are not along the diagonal are bad. And we'll just take this visualization and these crosstabs and look at some different models and see when they work and when they don't, and why they do and why they don't. So it turns out that linear regression is a neural network with no hidden layers and the linear activation function. So I have a bunch of inputs, x1, x2, x3. I multiply them by weights. I add some bias term, and I just add them up. That's linear regression. So I can do that in Keras. That's just a dense layer. So if I define a model that's just a dense layer with 10 inputs, or 10 binary digits, and 4 outputs, that gives us a linear regression model. And if I compile it with mean squared error loss and train it, this is the outcome. With binary inputs, it learns to always predict the number, except the best it can do. There's not enough representational power there for it to figure anything better out. With the decimal, it does a little bit better. As you can imagine, when you have the decimal representation of a number, it's very easy to figure out when a number is divisible by 5 and when it's not. And so it learns to always predict buzz when a number is divisible by 5. And so it gets the fizz buzzes wrong, but it gets the buzzes right. So that's cool. And this is what I just said. It's easy to learn divisible by 5. Similarly, you can do a logistic regression as a neural network. It's basically the same thing, except at the end we pass it through a logistic function. In this case, because all we're doing is looking what is the output with the largest value, it's essentially the same model with just a slightly different loss function, and so it learns basically the exact same thing. Again, it always predicts the number for the binary inputs, and it always predicts buzz when something's divisible by 5 for the decimal inputs. So those are not very interesting models, but now we can get into the sort of models that you actually need, a Keras or a Tensorflow or a Theano for, the neural networks with hidden layers. So here's a pretty simple, one hidden layer vanilla neural net. You can see it's got a dense layer, an activation layer, a dense layer, and then a softmax layer. Softmax is just a way of taking the outputs and turning them into probabilities. And from here on out, I'm only going to worry about the binary inputs because the decimal ones actually, they're good at learning divisible by 5, and they're really terrible at learning everything that's not that. So here's what happens when you train the one hidden layer network with various numbers of hidden neurons. So you can see with 5 hidden neurons, it doesn't learn anything. Again, not enough power. At 10, it starts learning a little bit of things, but still is not doing very well. Once you get up to 25, then it's actually doing pretty nice. It's only got 6 of them wrong. And you can see as you go on, it kind of bounces around a little bit. It tends to overfit to the training set. So even as you add more neurons, it's still not getting perfect because you've overfit to the training set each time. And then, the last thing to try is deep learning. It's pretty trendy, and everyone wants to do deep learning. So to do deep learning, we just add another hidden layer with some dropouts, which will help us with overfitting. But again, that's all it takes to set up the model in Keras, and then you train it the same way. So what happens if you do these hidden layers? If you do 100 in both hidden layers, you get to about 95% accuracy in the training set. And when you get to 2,000 by 2,000 hidden layers, then you can get it exactly right. But there's some randomness involved, so it doesn't always work. Okay, I got a neural network that can, solve this Fizz Buzz problem. I give it a binary number, and it figures out, is this number divisible by 5? Is it divisible by 3? Is it divisible by 15? That's cool, but if you said to me, hey, I want you to give me some weights that will take binary inputs and tell me whether they're divisible by 15, I'd have no idea how to do that. So I was curious, can we look under the covers and see what these are actually doing? Obviously, when you have 2,000 units in the first hidden layer, 2,000 units in the second hidden layer, you're talking about millions of parameters, and you're not going to have much luck trying to make sense of them. So what's the simplest model we found that was actually interesting? The simplest model was this 25 hidden neuron neural net. It got all the divisible by 15 exactly right. And so I wanted to understand, okay, I have all these binary inputs. How is it learning divisible by 15? Like, it's doing something kind of interesting, but what? What's it doing that's interesting? So I said, okay, one way I can approach this is to say, before I do my softmax, every input is spitting out 4 numbers. And so I could just ask, what are the inputs that spit out the largest number in that Fizz Buzz column? So I just took all my inputs, 1 to 1024, and sorted them by the output in that last column. So you can see 450, 390, 270, 330, 300, 780, 480, 360. And these are all divisible by 15, which is good. I mean, this way doesn't have to work. All you really need, because we're doing softmax, is for that last column to be bigger than all the other columns. But here, when you just look at which inputs make that last column the biggest in an absolute sense, you get a bunch of divisible by 15s, which is nice. So clearly, it's learning this divisible by 15 means stick something large in the last column. Okay, well, how's it doing that? One thing to notice, or one thing that you will you might notice if you stare at this for a long time is that you get a lot of pairs that differ by 120 that get almost identical outputs. So if you look at what is the output for 450, it's very close to the output for 330, which is 120 less. Okay, what is the output for 270? It's very close to the output for 390, which is 120. And so whenever I had found these two pairs of numbers on the previous page that differed by 120, they were producing very similar outputs across the board. And so why would it be doing that? And so I thought about it some more. And I realized if you have two numbers that differ by any multiple of 15, then necessarily they have the same Fizz Buzz output. If one's divisible by 15, the other one will be 2. If one's divisible by 5 but not 15, then the other one will be 2. If one's divisible by 3 but not 15, the other one 2. And if it's not divisible by either, neither will be the other one. So if you had a network that could learn to ignore differences that are multiples of 15, or multiples of 30, or multiples of 45, then that network would have a real head start towards learning how to predict Fizz Buzz. And it would only have to learn, in an extreme case, if you had a network that always did the same thing whenever two numbers differed by 15, and it did the right thing when it saw 15, then it would automatically do the right thing for every multiple of 15. Right, so there's very few equivalence classes for 15. So I said, okay, 450 was like the largest value of that fourth output. What are the other inputs whose outputs are closest to that 450 output? So this is a very awkward title for a slide. I couldn't figure out a better way to reword it. But these are the inputs for which the outputs are closest to the output for 450. And so I said, okay, how does each of these things relate to 450? Well, if I look at 330, and so I looked at what are the binary representations of these things. If I look at 330, it's plus 8 minus 128 from 450. So it basically takes the fourth bit and the eighth bit and flips them. If I look at 195, it's plus 1 minus 256 from 450. So it takes the first bit and the ninth bit and flips them. And if I look at 480, it's minus 2 plus 32 from 450. Again, it takes the second bit and the sixth bit and flips them. So what I discovered when I dug into this is that there's actually a lot of, I'll call them bit flips, where you take two bits and swap their values, that end up being multiples of 15. And so what that means is if you have a network that treats those two bits the same, then whenever you get those differences of 120 or whatever, the network's going to do the same thing on those. And it certainly looks like that's what this network learned to do. And so to take it even a little bit further, let's just look at what happens when we flip those two bits for a bunch of different inputs. So if I take 8 and I flip the plus 8 minus 128, I get to 128. You can see that the outputs of the last dense layer look almost identical. 9 to 129, again. 10 to 130, again. And for every one of these pairs where I got there by flipping those two bits, I got basically very similar outputs for the entire network. And now, 11 and 12, they don't look anything alike. 12 and 13, they don't look anything alike. But somehow the network has learned, I'm going to ignore all these 120 differences that are gotten this way. And that's actually happening earlier in the network too. I feel sort of guilty for making you stare at big tables of numbers, but this is the output of the first dense layer. If I look at 8 and 128, the bold ones are the positive numbers, and they all are pretty close. If I look at 15 and 135, the bold ones are the positive ones, and again, they look pretty close too. So it seems like that's really what this network is doing, is learning, is identifying these differences of multiples of 15 that I can identify by flipping a bit and then just learning to ignore them. And this also kind of suggests one reason why binary encoding does a lot better for all the non-divisible by 5 problems, which is that if I can learn that flipping this one bit should stay the same, well, that's going to help me, produce the same thing for 8 and 128, for 330 and 450, for a lot of different inputs. Whereas if you look at what would I need to learn in the decimal world, well, suddenly I'm not flipping bits, I'm turning 2 off and turning 2 on. And for 8 and 128, the 4 bits I have to touch are totally different from 330 and 450, the 4 bits I have to touch. So I can't learn these like simple flips that work for large swaths of numbers. I have to learn individual shifts, and it's much more difficult. And it's not a very complete explanation, but it's subjective, and I thought it was pretty interesting. So what were my lessons learned from this project? One, it's hard to turn a joke blog post into a talk. 2, feature selection is really important, but we already knew that, so that's not really a lesson learned. It's a lesson reiterated. Also, stupid problems sometimes contain really interesting subtleties, and sometimes black box models will reveal those subtleties if you look at them in the right way. And if anyone came expecting just purely a joke talk, I apologize that I included actual science and data and things like that. And that's what I've got. So the code is up on my GitHub. It's not in a great state, but I'll get it in a great state. If you want to find the blog post, it's on my blog. I'll tweet out a link to these slides after this talk is over. And there's a small possibility I might add a chapter about the slides to my book, so you should probably buy that just in case, too. And with that, I'll take any questions anyone's got. So the question is, have I thought about applying LSTMs to this? And the answer is, at this stage in like my deep learning practice, I'm really good at like dense layers, but I haven't really wrapped my head around LSTMs and recurrent networks and memory networks and things like that. And so I'm like, I'm trying to learn all that stuff, but I'm not at the point where I would have tried it on this problem yet. But I will. Right. Okay, so the question was, have I thought about taking this trained network and applying it to other problems? And the short answer is that the networks I've been playing with don't even get Fizz Buzz exactly right. So I'd be surprised if they did real well on other problems that are further away from it. But it's an interesting idea, and I'm going to go think about it. But I haven't thought about it much. What is Fizz Buzz Plus? Oh, no. I mean, I think there's a good point that it's easy to think of a broader class of problems, which is here's a pattern and like here's a pattern and some examples and figure out the pattern. And here, it's not really taking advantage of that. It's just like here's a dump of 1,000 examples. Can you predict 100 more? But with some of the interactive sequential learning, it could do similar problems like that. It's not obvious to me why the math would make it harder, but it's possible. So when okay, so there's what I would say is I was trying to represent it as basically zeros and ones, whereas prime factorization. I mean, you then it's suddenly like you got to get the powers of it in that representation, right? So I mean, there's no reason you couldn't do that. Um, like my gut tells me that I don't like taking data where it's like two means two factors of three, and three means three factors of three, and four means four factors of three, and putting it into like a neural network type model. But I can't really give you like a good explanation for that. Like just somehow my gut feeling is that like that's not a right representation. Um, Yeah, so the suggestion was to train one network just for divisible by three and another network just for divisible by five, and then just combine the two. And so, so a couple things. Yes, it feels like that might work. Um, two, that kind of falls along the. It's closer to what I call cheating, which is not cheating, but which is I know a lot about this problem, so I'm going to design a network that's really geared towards this problem. Uh, yeah, I think that would probably work, but I haven't tried it either. Any other questions? All right. Thanks everybody for coming.